Lecture number 6, Soil Compaction. Soil has three main components. So a soil sample is consisted of air, water, and solid particles. And when we compact soil, it means that we remove air from soil using external force. So we have a loose soil sample. Using external force, we remove air from our soil sample, and that is referred to as compaction. When all the air is removed from a soil sample, now when we apply external load, water is being removed from our compacted soil, and this is referred to as consolidation. So, removal of air from the void space in soil is compaction. When we have a compacted soil, fully compacted soil, it means that there is no more air between the particles in the soil sample. Now, with applying external load, what is being removed from our soil sample is pore water. So the process of pore water escape from the soil system is called consolidation. And that's the difference between compaction and consolidation. Compaction is the removal of air from a soil sample, and consolidation is the removal of water from a compacted soil. Consolidation is usually observed when we have fine grained cohesive soil. It's a function of time. It happens during the service life of a structure because, again, fine grained cohesive soil has very low permeability. So it takes longer for water to get out of the soil, and that's why it's a function of time, and it happens slowly. Again, because of the low permeability of soil. So now let's look at the relationship between soil compaction and weight. So we want to see what happens. How does compaction affect weight of a soil sample? Again, we have our loose soil sample. Apply external force to remove air and to compact our soil. So we have a loose soil sample and we have a compacted soil sample. The volume for our loose soil sample is 2 cubic feet and the total weight is 200 pounds. Unit weight, or gamma, is weight of soil divided by its volume. So for our loose sample, unit weight is weight 200 pounds divided by volume, which is 2 cubic feet. So unit weight of loose soil is equal to 100 pound per cubic feet. Now, when we compact our soil, volume is, we want to see what happens to volume and weight. Weight of soil sample, if you remember, air doesn't have weight. Weight of air is 0. So when air is removed, there is no change in total weight. So we still have the same weight, which is 200 pounds, but we observe a decrease in the volume of our soil sample. So we still have the same weight, 200 pounds, but now volume is decreased from 2 cubic feet to 1.5 cubic feet. So the unit weight of compacted soil, now it's equal to 200 pound divided by the new volume, which is 1.5 cubic feet, and that gives us 133.3 pound per cubic feet. So what happens here is that compaction results in a higher unit weight. Level of compaction is proportional to weight of solid per volume weight of dry soil per volume, which is dry unit weight. Why do we care? Soil's strength has something to do with the level of soil compaction. So that's what is important for us. Level of soil's compaction. If we compact our soil, and if we even fully compact our soil, it will result in an increase in the strength. The soil's bearing capacity will increase, which means that we can construct larger structures, heavier structures on that soil. It will also help with limiting the future settlements. So it will reduce the movement of particles, and therefore it will limit the future settlements in our soil and therefore in our structure. So the level of compaction is often specified in a contract document to secure a certain amount of bearing capacity, especially for road construction. That's the next test that we will look at. And using that test, what we will try to find is how to achieve the maximum dry density. And we said that this represents the maximum level of compaction. How can we achieve the maximum level of compaction? We do the test to see how we can achieve the maximum dry density. So this section that you see here is from a geotech lab report, and it says that it has a recommendation. All structural fields should be placed in thin lifts and compacted to a minimum of 98% of the soil's standard Proctor maximum dry density at optimum moisture content. And that's what we will do next. Find the optimum moisture content that yields the maximum dry density or maximum level of compaction. What are the parameters affecting level of compaction? One of the most important one is how much water we have in our soil. So moisture content is an important factor. A certain amount of water. So when you have a dry soil, it's hard to compact. When you add water to the dry soil, it acts as a lubricant, helps with the movement of particles along each other, and helps with achieving a higher level of compaction. So if we look at level of compaction or maximum dry density versus moisture content. At the beginning, when we have very low moisture content, we have a low level of compaction, low dry density. When we increase moisture, it keeps going up. So at the beginning, moisture helps with the movement of particles along each other and achieving a higher level of compaction. But at a certain point, after the soil is fully saturated, because water is not you cannot compact water, then it starts to have a negative effect on the level of compaction. This is with an increase in moisture content. So too much water results in an adverse impact, a negative impact on the level of compaction. So it's important that we find the optimum water content that gives us the maximum level of compaction or the maximum dry density. Another important factor is the compaction force, the type of equipment, the type of force that is applied, or in general, compaction energy per unit volume. Also, type of soil, if it's well graded, if it's poorly graded, if it's a coarse material, or if it's a fine material. These all are important and has an effect on the level of compaction. But in this lecture, we try to find the optimum amount of water, so the optimum moisture content that gives us the maximum density, dry density, or the maximum level of compaction. That's what we want to do next. So our next lab will be on compaction, and it's called standard Proctor compaction test based on ASTM D698. The objective is again to find the optimum water content that yields the maximum density, dry density, or dry unit weight. That is the objective of this test. So the test has a hammer. The weight of the hammer is 5.5 and the drop height is 12 inches. Then we have a mold, an extension for our mold. We place our soil in here and use the hammer to compact our soil. This is the standard Proctor compaction test, which is what we usually use in lab to evaluate level of compaction and to find the optimum moisture content required to achieve the maximum level of compaction. But if the standard test is not enough based on the properties of our soil, we also have a modified Proctor compaction test that uses a heavier hammer that is dropped from a longer distance. The rest is the same. This one is for higher values of dry unit weight. So this is the hammer. Again, weight of hammer is 5.5 pound, which is equal to 2.5 kilograms, and it's dropped. So we use this container to make sure that we are following the correct height of drop. So the hammer is dropped from 12 inches on top of the soil. This is the mold that we use. Put soil in the mold in 3 layers. First layer, compact 25 number of drops. Put the second layer of soil, another 25 number of drops. Add the extension and then do the third layer of soil and 25 number of drops. So 5.5 pound from 12 inch, 3 layers of soil and 25 number of drops per layer. Again, this is our mold. We do the first layer, put the first layer of soil in there. This is our hammer. This is 5.5 pound. This is 12 inches. We do put the first layer of soil in here, 25 number of drops. Do the second layer, 25 number of drops. Add the extension and do the add more soil and then compact the third layer. First, we need to prepare our soil. The soil that we are using is passing from number 4. So the material we need for this test is finer than number 4. You have your soil sample. Start by adding water. So we usually start with a dry sample. Then we add around 5% water. Based on the dry weight, we can calculate weight of water to have 5% moisture content. Then we compact our soil in the mold using the hammer that we have in 3 layers and 25 number of drops per layer. And after you're done with the compaction, we use one of those small cans. Get some of our soil sample from here, put it in this small can, and calculate moisture content of our soil. We also know weight of this mold when it's empty. After we're done with the compaction, we calculate weight of mold plus compacted soil. From the difference between these two, we can calculate weight of compacted soil. So again, we start with a dry soil, add around 5% moisture content, and then start compacting in 3 layers, 25 number of drops per layer. After we're done with the compaction, we need to do 2 different measurements. First, we have weight of empty mold and weight of mold plus compacted soil. The difference between these two gives us weight of compacted soil, or W here. We also know what is the volume of this container. So volume of compacted soil is equal to the volume of mold. Volume of compacted soil is equal to the volume of mold. This mold here. And that's our volume. Using these two numbers, we calculate unit weight, moist unit weight of our soil. That's the first measurement that we need to do. Second, we need to do the small can thing to calculate moisture content of our soil. Now that we have wet unit weight and moisture content, we can calculate dry unit weight. So at this point here, we have our first data point, moisture content and corresponding dry unit weight. So basically, we know that, for example, with 5% moisture content, what would be our dry unit weight? Then we put everything back in our tray, add another 5 to 10% moisture content to our soil. So now we can be anywhere between 10 to 15% moisture content, and we repeat the test. We need to repeat this test multiple times because we are again trying to make this curve, gamma D versus water content. So we have our first data point with approximately 5% moisture content. Then we need to add more water and see what is our dry unit weight at 10%. So we need to repeat this test until we see that dry unit weight. So at the beginning, dry unit weight keeps going up. At a certain moisture content, when we add too much water to our soil, it starts going down. That is when we stop. So there is no fixed number of trials. We need to repeat this test multiple times. We stop when we have a data point where dry unit weight starts going down. So we repeat with different water contents. Then we can make our compaction curve. And then we can find the peak of our curve, and that's our optimum water content, which gives us the maximum dry unit weight or the maximum level of compaction. So this is what we are trying to make. Our y-axis is dry unit weight, and you can calculate dry unit weight by dividing moist unit weight by 1 plus water content. And our x-axis is water content. Then we have our data points. And again, you need to repeat the test multiple times. Keep adding water to your soil and do another trial until you see that dry unit weight starts going down. That's when we can stop the test. Then we fit a polynomial to our data points, and then we can find peak of our curve. So this is what's important for us. That's the point corresponding to the optimum water content that yields the maximum dry unit weight. And this is the maximum level of compaction. This is Okay, so we start with materials passing from sieve number 4. And we add water to our soil, mix it very well until we have a consistent sample. Then we use the Proctor apparatus. So this is, as you can see, we have 2 hammers. The smaller hammer is for the standard Proctor test, and the larger one is for modified Proctor test. This is the mold we need to use, and these are small cans so that we can find the moisture content of our soil. So you need to measure weight of mold with the base plate when it's empty, and don't add the extension at the beginning. Put first layer of soil in the mold. Use the hammer to compact soil. Make sure that you move your hammer around the surface of soil to have a uniform compaction. This is the first layer, 25 number of drops. Then you add more soil and do the compaction for the second layer. Then you add your extension, add more soil, and compact the third layer of soil. Then you need to remove the extension and use a spatula to flatten the surface of your soil in the mold. Remove any excess material from the outside the mold and measure weight of mold with compacted soil. Then you get one of these small cans and took a sample to calculate moisture content of the soil. So that's your first trial. Now you put everything back in the tray, add more water to your sample, and repeat the process. Let's go over an example to calculate dry unit weight based on the numbers that we have from a standard Proctor test. So we have this mold. Volume of mold is 1/30th of a cubic feet. Volume of mold is 1/30th of a cubic feet. And weight of mold when it's empty is 4.35 pounds. Then we compact soil in 3 layers. And now weight of mold plus compacted soil is 9 pounds. What is the dry unit weight? So the difference between these two numbers, weight of mold plus compacted soil minus weight of empty mold, gives us weight of compacted soil. This is how we calculate weight of compacted soil. And remember that I said volume of mold is equal to volume of compacted soil. So you divide weight of mold plus soil, weight of mold plus soil minus weight of mold gives you, this is weight of compacted soil. And this is volume of compacted soil. Compacted soil. Which gives us wet or moist unit weight of our soil. The question is asking for dry unit weight, so you need to use this formula, wet or moist unit weight divided by moisture content. Moisture content is also given to us, 12%. So you can use these to calculate, use this formula to calculate dry unit weight. This is the calculation you need to do for each trial. So when you do the test in lab, you end up with this table. We have 1, 2, 3, 4, 5 data points. So we repeated the test 5 times. We have a set of laboratory compaction test data, and results is tabulated as follows. Determine the soil's maximum dry unit weight. So we are looking for maximum dry unit weight, gamma D, and optimum water content. So we need to make this chart, gamma D versus water content. Water content, we have 5, 10, 15, 20, 25. So we have 5, 10, 15, 20, 25. We have 112, 115, 115, 113, and 109. Then we need to fit a polynomial and find our peak. But you need to do all of this in Excel. So you do all the calculations in Excel. And then you have these two rows. Water content is our x-axis, and dry unit weight is our y-axis. Select your numbers, go to Insert, and select Scatter with only markers. You'll have this chart. Then you can add title, X title, and Y title. You have water content in percentage and dry unit weight in pound per cubic feet. Then you add minor grid line to your Y axis. That makes the reading the numbers easier. Then you click on your chart and add trend line. Make sure that you select a polynomial. So we are adding trend line. It needs to be a polynomial with the second order. And that's your chart. So the question was asking for optimum water content that yields the maximum dry unit weight. So you need to find peak of your curve. Then this is your optimum water content that yields the maximum dry unit weight. You need to do all of this for your next homework in Excel. So, after we're done with the compaction in field, how can we confirm if we achieved the level of compaction that was mentioned in the contract? So, in most specifications for earthwork, the contractor is instructed to achieve a compacted field dry unit weight of 90 to 95% of the maximum dry unit weight. So we do the lab tests, come up with the maximum dry unit weight, and then in the contract, usually the contractor is required to achieve 90 to 95% of that maximum dry unit weight. But how can we confirm that that level of compaction and the maximum dry unit weight is achieved? There are different tests that can be performed, but I have a simple test, a very simple test that can be done on site in field to measure the dry unit weight of compacted soil. So we need to use a certain type of sand. It's called Ottawa sand. And we have this container. So we have a jar that has a cone here, and there is a valve here. We fill out this jar with sand, Ottawa sand, and then we make a hole. So this is our compacted soil. This is our compacted soil. We make a hole, remove this soil, and measure weight of compacted soil. We just remove it from there, put it in a container, use a scale to measure weight of soil here. But in order to calculate unit weight, we also need to know what is the volume of this soil, compacted soil that we removed from there. So what we do is that we have a jar that is filled with Ottawa sand. We make this hole, place our jar on top of this hole, and open this valve. We don't touch it. Let the sand to move into this hole. And when it's completely filled, we close the valve and remove the jar. Measure weight of jar with the remaining sand. So now we have this much sand. We have, using this technique, what we get is weight of sand in the hole that we made. We have unit weight of sand. We know this. We can calculate volume of sand in hole that we made, and volume of sand in hole is equal to the volume of hole, which is equal to the volume of compacted soil that we removed from the hole, which is this one. So now we have weight of the soil that we removed from the hole. We also have volume of the soil that we removed from the hole. We divide them by each other and we have unit weight. We can also use the same technique with the small can to calculate water content, and then using these numbers we can calculate gamma d as gamma divided by 1 plus water content. And that's like a simple technique that we can use to measure density of soil in field. So this is the jar that we can use. It has a cone. We fill this jar with a sand and we know what is the specific gravity of that sand. I'm sorry. Then we use the apparatus that you see here to make a hole. Place that soil in a container. Then we can measure weight of the soil that we have in the container. Then we put the jar with sand, open the valve, don't touch it. There shouldn't be any movement close to the jar. And just let the sand move from the jar into the hole. Then close the valve and remove that. So we need to do some type of correction for the amount of sand that we have in the cone, but we already know that. We just need to measure now the new weight of cone, jar, and the remaining sand. And using this information, we can calculate moist unit weight. Knowing the moisture content, we can calculate dry unit weight, or we can dry this soil sample and then calculate dry unit weight.